So we will, as I see that everybody comes relatively rapidly from the coffee break, we can start not too much late time. And we will start with Christian Beaugé from the Institute of Astronomical, Theorical et Experimental of Observatorio Universidad Nacional de Córdoba in Argentina. And he will speak of multi-body resonance in exoplanetary systems.
Thank you. Welcome. I would like to first thank the organizers for the invitation. It's my first time here in Salt Lake, and so it's an honor to be here. So I will speak about multiplanetary resonances, and the thing that motivated me how to give this talk is the story of TRAPPIST-1. So not so much the system as we know it today, but how this evolved during the different phases of discovery. So, okay, you all know, initially in 2016, the Dynamical first detection by the transit team around an ultra-cool star. So originally there were 3 detected planets. The first 2 very close to the star, periods 1.5 to 2.4, almost Earth masses, and there was an indication of a 3rd planet, although it couldn't be constrained. Okay, several periods were suggested. The most probable was about 18 days. So with new observations, the following year, this year, Elon found that what was thought to be TRAPPIST-D was actually the combined signal of 4 different planets. So this gave origin to 6 planets now, and there was also indication of a 7th planet, although once again it couldn't be well constrained. Now, interestingly, when you take all these orbital periods, it seems that they are in successive mean motion resonances. So planet E and planet C are in the 8 to 5, C to D in the 5 to 3, etc. Then came Luger et al. A bit later this year, just a few months ago, they did additional determinations, observation with Kepler, but before analyzing this data, they did something which was very interesting. They said, okay, so we have this system which is locked in 2-body resonances, but you can also write this in another way, saying that it is actually locked in 3-body resonances. So the first 3 planets are locked in a 2 minus 5 plus 3, the next, the second, third, and fourth in a Laplace 1 minus 3 plus 2, etc. Okay? So this is an interlocked 3-body resonance, usually referred to a resonant chain, and each of these pieces are Laplace or zero-ordered 3-body resonances in which a relationship is given by integers p and q such that the sum of these integers is 0. So why not the position of the last planet also in a 3-body resonance with the other systems? Okay? So they tried that, and from the new observational data, they tried to see what values of P and Q were more consistent with the observations, with the signals. And they found apparently that the best choice was P and Q equal to 1, which gave a planet with a period around 18 days, which was one of the first options for the original 2016 fit. So now we have the system, 7 planets interlocked in a 5 zero-order 3-body resonance, which is a very remarkable, very unique system. Okay, this is not yet confirmed. When you do numerical simulations with initial conditions compatible with the observations, most of them, practically all of them, are unstable on short timescales. However, as with transit systems, the masses, eccentricities, and longitudinal center are very uncertain and unknown for planet H, so this is not really surprising. Another way to try to see whether this is actually real is to do planetary migration. So basically, you take planets far from the resonance, or at least partially far from the resonance, and then you evolve them and see whether they are captured in configurations which are compatible with the observations. And in this particular case, you had a capture in all the resonances, and you have libration both of all the two-body and all the three-body resonant angles. So this gives a certain confidence that what you're observing may actually be real. Okay. So it is a very remarkable and very unique system. So why were 3-planet and not 2-planet resonances used as proxy? Okay. So if you have a 3-planet zero-order resonance, you can write this as 2-planet resonances. If you have 2-planet resonance, you can write it as 3. So why not just continue using 2-planet resonances? Okay. So trying to answer that is what I will try to address in this talk. Okay. Now, multi-planet resonances are rare. Okay. We know that 2-planet resonances are uncommon, particularly among closed-in systems. This is a histogram mostly showing the orbital period ratio. And okay, you see some accumulations, particularly near the 3-2 and 2-1 resonance, but most of the systems appear not related to two-body resonances. Okay? And people have said, okay, you have to use or assume stochastic forces that could have destroyed many or most of the primordial captures. Things are even worse when you have more than 2 planets in a resonance. These are expected to be even more rare. Okay, so you have simulations by Tidally 2013. You see data from this year showing that, okay, you may capture multi-planet resonances while the disk is still active, but when it dissipates, the eccentricities begin to increase, they become unstable, and if you include even all these stochastic forces, most of them are destroyed. Still, several can survive. And maybe those are the ones we can see today. So the well-known cases that we know of multi-planet resonances in the giant planets, well, at least A76, which has been widely studied over the past several years, HR 8799, which is not yet confirmed, apparently is also in a Laplace-type resonance, and particularly in the last few years, several systems have been found in Kepler. Kepler 60, 6 planets, 80, and 2 to 3, 4 planets each. Again, you have 2 3-planet resonances and a 4-planet resonance. Now, we know that for radial velocity systems, we have a fairly good idea of the masses and the orbital elements, so you can do very detailed dynamical studies. Okay? So, for example, you can dynamical map of the position of the outer planet of Gliese 876. So this is eccentricity versus the orbital period. This is the Megno chaos indicator, and we see a small, apparently more regular region near where the planet is located. However, when you do a zoom of this region, you see that this region is actually much smaller. The best fits presented by Rivera and Baloev are borderline on this low chaoticity region. And actually, if you do an even a greater zoom, you see that the whole region is highly chaotic, except for this part, which looks very strange, very fractal, which has chaos or Megno, which is always larger than 2, but is much smaller than this red region. Okay. So this is the actual inner resonance zone of the Laplace resonance in Gliese 876. All the orbital fits are outside. If you take initial conditions in different parts of this plane, outside, inside, and in these like rivers, you find completely different Lyapunov exponents. You have widely and very chaotic systems outside, including the orbital fits that are presented. So these fits are extremely chaotic, although they are stable. You have intermediate chaos in these like rivers, and you have lower chaos in this inner resonant region. You can also plot the resonant angles, and we see that both resonant angles of the inner two-body resonance of the pair are librating. For the outer pair, one of them is librating, the other not, and the Laplace angle is also librating. Since the Laplace angle can be written as a linear combination of the resonant angles of the two-body systems, then actually this dynamics is defined on one hand by what is called the true or pure three-planet resonant dynamics plus the double resonance terms. And it is this interaction of different resonant terms that generates this extended chaotic region and very small stable ions. Okay. So we can do many things for radio velocity Doppler systems. What can we do for transit systems? Okay. Once again, reliable values for the eccentricity, longitude and pericenter are not available. So if you want to study two-planet resonances, it's very difficult, even with precise values of TTVs. So the question is, can we do better for three-planet resonances? So is there a certain way that we can prove that the Laplace angles are liberating in transit systems? And the answer is yes. And this is a very interesting paper by Menz et al. For Kepler 223. Again, for planets, not surprisingly, you have 3 two-body resonances, 2 three-body resonances, and 1 four-body resonance. Okay, so forget about these. We can't do that for transit. But what about these? The interesting thing is that independently of the resonant dynamic being dominated by the true three-planet resonance or by the true two-planet terms, these angles depend only on the mean longitude, do not depend on the longitude of the pericenter. So if you assume that the eccentricities are small, you can actually calculate this mean longitude directly as a linear function of time in terms of the orbital period of the planet and of the mid-transit time. So if these quantities are constant, the orbital period is constant, you will have a linear function of the mean longitude. But if you have TTVs and you're able to include the variation of these quantities into your model, you're able to have a very precise description of the evolution or the mean longitude suffered by the perturbation of the planets. And then you can estimate, even measure, what would be the time evolution of these Laplace angles. Okay? So this is possible if you have, on one hand, very precise TTVs, and on the other hand, a long observational time span. And this is what these guys did. This is a 4-year time span of observations. This is the Laplace angle of the inner three-planet resonance, outer, and of the four-planet resonance. And you can see a libration, apparently, around values which seem to be asymmetric. Okay? So it's not a complete period, it's only 4 years, but there is a very strong indication that these angles are in fact librating. Another way to prove this, you can do simulations of migration, and then you can see, once they're captured, what are the equilibrium values of these 3 angles, and they coincide very well with the predictions of those observations. So even though we cannot confirm completely that this system is inside Laplace resonance, the libration could be temporary, it appears to be so. There's strong evidence indicating that this system is in fact locked in a multi-resonant configuration. Okay? So that's the main advantage of working with three-body resonance with respect to two-body resonances in transit systems. Okay? They appear to be tailor-made for these cases where we only know the orbital periods, but with extremely precise precision. And we don't know the masses, we don't know the eccentricities, and we don't know the longitude of the pericenter. Okay? And this technique is being planned for other Kepler systems, of course, and even for TRAPPIST-1. Okay, the rest of the talk I will try to discuss the following questions. What are the routes for capture into multi-planet resonances? How do tidal interactions affect these resonant configurations? And where do we expect to find present-day multi-resonant systems? In double resonances or in pure n-body or three-body resonances? Okay. In order to attack these questions, I will use dynamical maps. So basically, I am choosing equal masses for the planets, initial conditions which are circular, full planar, and angles equal to 0, grid of initial conditions in P2 over P3, orbital period ratio, and P1 over P2. Each initial condition is integrated for 10 to the 4 orbital periods of the outer body, and we plot values of maximum delta A. So red values are large, maximum delta A, associated with or instabilities or separatrix, and small values are more secular and more regular solutions. So what kind of features can we identify in these dynamical maps? Well, the simplest thing is two-planet resonances. So you have in almost horizontal lines, resonances between body 2 and 3, almost vertical lines, two-body resonances between body 1 and body 2. You can also see these curves, which are two-body resonances between the inner and the outer planet. Okay? And that will prove to be important further on. Okay, you can see also the true Laplace resonances, and you can see the separatrix as slightly lighter colors of blue, and you can model that with Akilin's 2011 model for pure 3 microresonances, and it seems to fit very well. And finally, you also see some additional lines, and these correspond to first-order 3-body resonances. They're much weaker, but they also appear in these plots. So,
why is it not straight line?
Because the plane, the dynamical map is in a representative plane of oscillating elements. The resonances are mean, so we have to transform them to oscillating to make a better fit. Okay. So, in this map, where do we expect to find resonance systems? Okay, so we can do some numerical simulations. If we begin with initial conditions, for example, in these 2 points, and we do a conversion migration, which is basically from the bottom left to the top right, and you can have different type of routes depending where the migration is slower or faster in each subsystem. So, for example, for this case, first you have the capture of planets 2 and 3 in the 3/2 resonance, and then you begin to move this subsystem until this is captured in the 3 with the other system. And the same thing occurs here, but you can have some preliminary or some temporary captures in different resonances.
2 points are 2 simulations?
Yes, there are 2 simulations. Yes, 2 initial conditions, 2 simulations.
Okay. Some dissipation there.
Yes, of course. Yes, yes. Migration. Yeah, you simulate migration with an n-body code and see what happens. Okay, so you have that these traps with the system, we can speak to be trapped, are usually defined by 2 walls defined by 2 tangent resonances. Okay, so that's where we expect to find these systems. And that's what really happens. Okay, so this is Kepler 60, that's the body there, and you have the 5-4, 4-3 resonance, and here you have the 1 minus 2 plus 1 3-body resonance. But what you actually see is that this system is not really in a true 3-body resonance. It's just in a double resonance defined by 2 2-planet resonances. The same thing can be done for Kepler 2-3. Once again, you have this system, and very interestingly, both of these subsystems, these trios, are intersected by the 1 minus 2 resonance between the inner and outer bodies of each triplet. Okay? This will also be proved to be important further on. So, given those final configurations, which you can attain in different directions, okay? So, the question is, does the final configuration depend on how the individual links are built? In other ways, if I begin with a system, and for example, my initial condition initially goes to there, and then it goes to there, or if it goes to there, and goes to there, or maybe this one goes first and this second, will the final configuration change? Okay? And there's a very nice paper by Tidally from this year that says, yes, at least for system Kepler 2-3. So what he did is construct an analytical 4-planet resonant model for the system and found that there are 6 independent stable solutions of the Laplace angles, all asymmetric. One of them corresponds very well with the observed values for the Laplace angles that were made by Niels et al. From last year. And apparently, the existence of these multiple solutions asymmetric is tied to the existence of first-order resonances between non-consecutive planets, which was that curve that we saw in the dynamical map. Now, which solution is chosen during capture is, of course, sensitive to initial conditions. The observed configuration, where it has these angles, has an average probability of about 25%. Okay? However, depending on the capture sequence, on how this chain is constructed, the probability may vary. So there are 2 extreme cases. For example, first, if the body 2 and body 3 are first captured, and then they capture body 4, and then finally they capture body 1. Then the probability of attaining the correct observed solution climbs to about 52%. On the other hand, if you have an in-out capture process, so first you captured the first 2 bodies, then the third, then the fourth, the probability of attaining the observed solution falls to about 4%. Okay? There's a big difference. And the most interesting part is that this type of in-out capture is this thing that you will more or less expect in an in-situ formation. Okay? So this is a bit of evidence showing that perhaps this system is favored by a, I don't know if long scale, but at least significant scale planetary migration. Now, I mentioned that traps occur in the intersection of 2 planar resonances. However, if you take very slow migrations, you can also have traps defined by pure 3 planar resonances. Okay, so this is one example. Again, initial condition. You migrate very slowly. The characteristic time scale of migration is of the order of 10 to the 7 years. And so you get captured in this first order resonance. It reaches an intersection and it switches to this other one. Okay, and it just carries on. However, under certain conditions, you may be captured again in an intersection, but this also acts like a trap, like a wall. So if you do the time evolution of the period ratios, you have the changes, the corners, but when they reach this intersection of 2, 3 body resonances, they just stop and just remain there forever. So this is stable, although 2 walls defined by first order 3 planar resonances are not so common. Now, the interesting thing of this is that if you have this type of system, it will be very difficult to identify. And it will be impossible to identify if you're just looking at the 2 planet resonances. Okay? So what we wondered is that, could it be maybe that there are more resonance systems among the Kepler planets, but just that they correspond not to the usual Cartesian Euclidean intersections? So we did some statistical study, which is very crude. We just superposed the distribution of the planets in one of our dynamical maps. So we make a zoom there because the results were better there. And we obtain this type of correlation. So you have several different first order resonances. And there seems to be a certain correlation between the distribution of the systems and these resonances. So it's that.
These are raw data or mean elements?
Raw data.
So you need to...
I cannot calculate mean elements. I don't have the mass. Yeah. Okay, so if we want to do that seriously, okay, we calculated what we call a proximity index, which we begin to make more complicated, but we don't know, we don't really have a model for these first order resonances, which is something we're currently working on. We don't know the eccentricities, we don't know anything. So this is all very crude, and apparently this correlation is not significant. Okay, the probability that this is just random is of the order of 1%, which is extremely high, and you can easily find other random distributions which seem very similar. Okay, so this is probably not true. Okay? So this is not true for the complete population, but it doesn't mean that it may not be true for some of them. However, again, even if some of these are in 3 planet first order resonances, we don't have the masses, we don't have the eccentricities, so finding them, proving they are, is extremely difficult. So, who knows? So the last thing I would like to discuss is, okay, we have these systems which are captured in these resonances. Let's go to the classical. So you have these walls defined by 2 planet resonances. What happens when you introduce tidal evolution? Okay. So you begin to have a divergence, migration. So the question is, okay, do they go back the way they came? Do they go by another resonances? What happens? Okay. And the solution is that they will go out by the true 3 planet resonances. Okay. And during all this process, the Laplace angles continue to vibrate. Okay, so you remain forever within the Laplace angle, even though you have ever more offset with respect to the two-planet commensurabilities. So why does that happen? Well, okay, if you have just a two-planet resonance, tidal evolution follows the loci of solutions, so there is no other way than to escape from the resonance, because the location of the resonance in the orbital period ratio is fixed. In the case of three-planet resonances, there is no fixed value for the orbital period ratio. So actually these resonances work more like trenches, like canals, or like roads that allow you to travel through them as you are migrating and varying your orbital periods. Okay? So they constitute natural evolutionary tracks for tidally evolved systems. It's something that Papalosio has studied a couple of times over the last couple of years. So, how do these apply to these three systems? Okay, Kepler 223 and Kepler 60, the inner orbital period is of about 7 days. Kepler 80 has much planets closer to the star. So if we find some tidal evolution, it will be for Kepler 80, and apparently we do so. We see that those two pair of planets are significantly displaced with respect to the crosses, to the intersections. They are evolving tidally. And this corresponds very well with the simulations by McDonald et al. For the system. So they did an initial capture of this system through a migration. They evolved towards the nominal ratio of orbital periods, and then they introduced tidal effects. They began to diverge again. They attained the observed ratio after a certain time, and even though they suffered significant offset, the evolution of both Laplace angles remain libration and with a very small amplitude.
Body resonant.
Huh? What?
Body resonant.
Yes, I know. Yes, but it's not a natural vibration. It's more a cinematic vibration. Okay? Yeah, it's different. There's no separatives. Okay, TRAPPIST-1 seems to be slightly evolved, particularly for this thing here. This includes planet H. Okay, so this more or less explains why it is better to fit the system to three planet resonances and not just to two. Okay, so a bit about the conclusion. So Kepler 80 and TRAPPIST-1 show evidence of tidal evolution, not so much 60 and 223. The important thing is that contrary to the two-planet case, the system remains in the resonance and the original configuration is not lost. You do not lose information about the origin of the system. And the idea is that you can write the offset from the two-planet resonances as a function of time in terms of masses and in terms of the quality factors. You're neglecting stellar price here, so it may not be such a good idea outside the double resonance, but you can then estimate either the values of Q or the planetary masses if you know the age of the system and how far they have evolved. Okay, so that's an idea which is very interesting. Okay, so I don't know how I'm doing with time. I think I'm doing well, so I will just finish with the conclusions. Okay, so these Laplace resonances are ideal to study in transit systems where you have very precise orbital periods, you have access to TDV, but probably nothing else. Okay? You can show or you can try to estimate the variation of the Laplace angle, so you can prove that this system is actually in resonance. Tidal evolution preserves the resonant condition and gives you some insight about what the tidal parameters or the masses could be. So that's very important. You can do a lot for these systems, even with very little information. Okay. The dynamics of this resonant chains apparently is very complex, particularly if you have interactions between non-contiguous planets. And finally, it is possible to capture in pure three-planet resonances, but you need a very slow migration, and maybe it is not a high probability for that. So, who knows? And that's it.
Thanks a lot. That was really nice. And we have time for questions.
Yes.
just one minute. In your simulation that you try to capture the bodies of the models, at least in the simulation, what sort of eccentricity do you use?
Low.
They are very close.
Low.
These systems in the Laplace should be anyway low eccentricity.
Yes.
They are very close to the star. They are very close to the star.
Yeah, but still, yeah. But anyway, when they tidally evolve, they go to zero practically.
But even without the tidal evolution.
Yes. So this is about 0.05, maybe a bit higher, maybe lower, but I mean not much higher. Anyway, you have to realize that these are all simulations, in-body simulations, right? Not hydrodynamic. So you more or less force the diameter to be a certain size. Okay? Yeah? It's not self-consistent.
Alexandre, this paper is published?
I have one question. The dynamical mass will operate with the equal mass.
Yes. Yes.
But then you put in this diagram all planets that have different mass rates. My question is how these dynamic function maps change when you change the mass.
Okay, yeah, the masses for the planets are not well known. Okay, the errors are typically 50%, something like that. They're not that difference in the masses estimated in TPDs. They're usually about 0.02 or maybe they get larger. Anyway, those maps are more for illustration purposes. Okay, show where the resonances are, show which are. Since we don't yet have a model for example, the first order resonances, we cannot estimate which are the strongest. And you have infinite number of resonances. So which are the significant ones? Okay, so these maps give you relative strengths of them. Okay, this is more important than the other. But they just serve for illustration purposes.
In a zero order free body resonance, because you don't have the PD, this means that the resonance width is not a function of the eccentricity.
Yes. Exactly. We don't. We couldn't find
You
it.
say that you
No,
can
first.
factor directly in free body resonance.
Yes, in first order.
In first order.
Yeah, not in zero order.
You
No.
never- So zero order
No.
resonances are always the combination
Exactly. Yeah.
of body resonance.
It's like a fence. Yeah. And okay. So the horse can go out. Not can.
This paper is published?
No.
When, Andrea? Oh, sorry.
When transmission is taking place and you do MMR crossing,
Yeah.
mean motion resonance
Yeah.
crossing, then it gets trapped at that point.
Sometimes yes, sometimes no. It depends on the strength of the resonance. It depends on the masses. It depends on the migration rate, and it's also probabilistic.
And then it comes out. It gets trapped for some
Yes,
time.
and it continues. Yes.
Andrea?
Can you try to translate this in terms of the regional Laplace resonance here, Europa Ganymede? I know it is currently the three-body resonance is locked, and the two-body resonance are circulating.
Yeah.
So
Okay.
what-
I have never worked with the Canadian satellites. Okay. This is it is a much more difficult problem. Okay. You have J2, which modifies the dynamic significantly, which we don't have in exoplanetary systems. Okay. This is a nice plot by Gallardo and collaborators from last year. Okay. So what they did is this is the first plot. Do I have time to explain this or not?
Yes.
Yeah, okay. So this is a dynamical map, eccentricity and semi-major axis of Europa. You're varying it, okay? You're keeping Io and Ganymede fixed. Right? And this is a place of Europa now. And you see certain structures, okay? So you see this black line, which apparently is a more regular region. And you see this other like curve, which apparently is another regular region, and you want to try to understand what is happening there. This is the libration of the Laplace angle, okay, the pure Laplace angle, okay? And you see this here, the Europa is right inside, okay? It has a finite width for zero eccentricity, which is exactly what he said, that when you have a zero order Laplace resonance. This here is the exterior resonance generated by Io on Europa, this part here. And this is the interior 2-to-1 mean-motion resonance generated by Ganymede. So up here, you have a combination of all those different resonances. And depending on where you are, the contribution of them is different. So since you lie inside the true Laplace resonance affected by the tail or the pericentric branch of the two-body resonance with Ganymede, the outer resonance with Io is very complicated, so it is sometimes difficult to evaluate. But so you see different structures there. Depending on where you are, the different terms are more important, and so they interact in a non-linear way.
So there isn't a unique way to build this resonance?
No. No.
So if I can comment, in a two-body resonance of first order, the pericentric branch is a continuous curve.
Yes.
So calling a body resonant or no resonant, depending if it is far away, separate, I think is a little bit, well, it's a matter of semantics, but
Yeah,
I don't think the body leaves a resonance just because the separate is far away, goes away. They call the pericentric branch is a continuous branch, so following the tidal evolution, just follow it. So for me, they remain in resonance, even if they are offset in the period, which is in agreement with the figure you just published.
Exactly. So the resonant terms still affect and sometimes dominate.
Yeah.
Yeah. Calling it resonant.
Yeah,
I don't know.
it's semantics.
Yeah, it's semantics. Exactly.
Well, it's a nice illustration to show that if you leave a lot of time, we have a nice discussion.